Cross-validation is a critical concept in machine learning that ensures your models perform reliably on unseen data. In this guide, we'll walk through its purpose, how it works, and why it's essential for building robust models. By the end, you'll understand how to use cross-validation to select the best machine learning methods and fine-tune parameters for optimal performance. Why do we need cross-validation? Imagine you're working on a medical dataset containing variables like chest pain, blood circulation, and other factors to predict whether someone has heart disease. When a new patient visits, you'll measure these variables and use your model to make predictions. But with so many machine learning methods available, logistic regression, k-nearest neighbors, support vector machines, and more, how do you decide which one to use? This is where cross-validation comes in. It allows you to compare different methods and evaluate how well they'll work on new data. The basics of cross-validation: training versus testing data. To build a machine learning model, you need to do two things. 1. Train the model. Use part of the data to estimate the parameters, e.g., fitting a logistic regression curve. 2. Test the model. Use separate data to evaluate how well the model predicts outcomes for unseen cases. Using the same data for both training and testing is a bad idea. It doesn't show how well the model generalizes to new data. A simple approach, splitting the data. A basic approach is to divide your dataset into two parts. 1. Use 75% of the data for training. 2. Use the remaining 25% for testing. While this works, it raises a question. 1. What if the 25% you selected for testing isn't representative of the overall data? 2. Could another split produce different results? How cross-validation solves the problem. Cross-validation eliminates this guesswork by systematically testing the model on all parts of the data. Here's how it works. 1. Divide the dataset into blocks, e.g., 4 equal parts. 2. Use a combination of blocks for training and leave one block for testing. 3. Rotate the testing block through all combinations. For example, 1. Start by training the model on the first 3 blocks and testing it on the last block. 2. Next, train the model on different blocks and test it on another block. 3. Repeat until every block has been used for testing. At the end, you summarize the results to compare the performance of different models. Comparing machine learning methods with cross-validation. Using cross-validation, you can directly compare machine learning methods based on their performance on test data. For instance, 1. If support vector machines consistently outperform other methods during cross-validation, you'd select it as the best option for your problem. This approach ensures your model will generalize well to new, unseen data. Types of cross-validation. The way you divide your data determines the type of cross-validation you're performing. Here are the most common types. K-fold cross-validation. 1. The data is divided into k blocks, e.g., 4 or 10. 2. Each block is used for testing exactly once, and the results are average. 3. Commonly used with 10 blocks, called 10-fold cross-validation. Leave one out. Cross-validation. 1. Each individual data point is treated as its own test block. 2. This is computationally expensive but provides a thorough evaluation. Custom splits. 1. Depending on your data, you can create domain-specific splits to ensure meaningful testing. Fine-tuning parameters. With cross-validation, some machine learning methods include tuning parameters, values that aren't estimated from the data but are set manually. For example, ridge regression has a parameter that controls regularization. Cross-validation helps you find the best tuning parameter by testing different values and identifying the one that produces the best results. Key takeaways. 1. Purpose of cross-validation. It evaluates how well a model generalizes to new, unseen data. 2. Process. Rotate through different training and testing blocks, ensuring every part of the data is tested. 3. Model comparison. Use cross-validation results to select the best performing machine learning method. 4. Parameter tuning. Optimize tuning parameters for methods like ridge regression using cross-validation. Putting it all together, cross-validation is a powerful tool for building robust machine learning models. It helps ensure that your chosen method isn't just good at fitting the training data but also effective at predicting outcomes for new data. Your next steps with AI Tech Nav. Now that you've mastered the basics of cross-validation, why not apply this knowledge to your projects? At AI Tech Nav, we provide resources, tutorials, and mentorship to help you navigate the world of artificial intelligence and machine learning. Subscribe for more guides, or join our community to connect with peers and mentors. Together, let's build a future powered by AI and technology. Until next time, keep exploring with AI Tech Nav.